Yeah, I hope my screen is visible. I hope I'm audible enough. In case of any questions, you can stop anytime. And I request Rajesh to relay any questions that shows up on the chat.
Sure.
Because I will be looking at the slides. And yeah, so thanks for the invitation to participate in this seminar series. It's nice that the pandemic has forced us to has resulted in such activities like E7. Like we can actually run a seminar series without really having people over. And I was telling Rajesh that it's an incidental honor that that it's the 50th talk. So yeah, it just happened that way. And it's also I like to commend Rajesh on actually sustaining this series for 50 lectures, because it's really not easy to keep finding people and contacting them and continuing the series, and that was a weekly series. Monthly series maybe still it's less effort, but weekly means every week one has to keep be on the toes. Yeah. So with that, I'll just go into the technical content of the talk. So the title is Sensitivity Conjecture and its Resolution. And this is a conjecture. This was a conjecture stated in the early 90s, and this was proved by Hao Huang, who is he's a mathematician at Emory University in Atlanta, USA. And it was a conjecture that was around early 90s, so roughly almost 30 years it remained open. And once it was proved, people were like amazed and spellbound by the simplicity and brevity of the proof, right? So the proof, he released the proof on arXiv mid 2019, and it was published in Annals of Math by the end of 2019. And some of my slides are inspired by Huang's slides that he gave in a seminar, in an online seminar. So yeah, just acknowledging that. Okay, so let's get started. Once again, if there are any questions, feel free to stop. Feel free to ask the question. Okay. So we'll start with a combinatorial question. We'll explain. We'll answer it, and then we'll see why this. Then we'll see why this is the same as the sensitivity conjecture, and then at the end, we'll probably see the proof that they are the same. Okay. But first, we'll see the question. We'll see the proof, and then we'll talk about the significance of sensitivity, and then at the end we'll see the connection if we have time. Okay. Okay. So this is the Boolean hypercube. Hypercube is generally so it contains, so it's a graph on 2 power n vertices, where each vertex is represented by an n-bit vector. The edges, there are edges between any two n-bit vectors if they're separated by a Hamming distance 1. Right? So what is there in the picture is Q3, the three-dimensional hypercube. Right? So you can see that 100 is adjacent to 101, 110, and 000, all the adjacent points with Hamming distance 1. And so it is a bipartite graph. All the odd parity vertices and the even parity vertices on the other side. So the edges are, all the edges connect an odd parity vertex with an even parity vertex. It's not that difficult to see. So right. And if you look at these vertices, this is all the odd parity vertices, the red colored vertices, they form an independent set, obviously, because it's one half of a bipartite graph, right? So now if I add one more, if I want to color one more vertex red, right? Let's say I color this one red. Right? I'm coloring blue, but let's say I'm coloring this one red. Now we have 5 vertices, but the induced graph by these 5 vertices has max degree 3, right? The blue colored vertex has 3 neighbors, right? So the question that we will ask is, on a hypercube, if I pick one more than half the vertices, so 2 power n vertices are there in the hypercube. So if I pick 2 power n minus 1 plus 1 vertices, right? What is the max degree of such a hypercube, right? So, but if I pick these 4 vertices and add one vertex, the max degree is 3. Okay, but this is not really that interesting because the graph itself has max degree 3. Okay, so now let's look at if I choose the 5 points like this, right, as in the figure. Now you can see that they form the induced graph is a path of length 5. So which means the max degree of the red vertices, the graph induced by the red vertices is 2, right, which is smaller than 3. And we can even add one more vertex, right? So include this vertex more. So you get an induced cycle on 6 vertices, again max degree 2, right? And you can see that whichever way you choose 5 vertices, the max, there is a vertex of degree at least 2. Right? You cannot get smaller than this. And we can ask this question in general, right? So this is Q3, the 3-dimensional hypercube. You can ask for Q4, right? So Q4 I have represented by Q3 here, and edges connecting the corresponding vertices. So this vertex here is adjacent to this vertex here, right? So there's no clean way to denote or represent it or pictorially represent a Q4. But now in Q4 there are 16 vertices. So the corresponding question is 9 vertices. What is the max? What will be the max degree? And we want to get a graph which has a small max degree. So I have already marked out 9 vertices, like 4 on the left side and 5 on the right side. And it may be difficult to see on this, but if I just do this, now you can see that these 9 vertices form an 8 cycle and an isolated vertex, right? So 8 cycle, so again the 8 cycle plus isolated vertex, the induced graph has max degree 2, right? So I took 9 vertices of a Q4 which has max, this 9 vertices has an induced graph that has max degree 2, right? And in any combination of 9 vertices, there is a vertex of max degree 2. And we can ask this for the next level and so on. So Q5, if you have to take 17 vertices, and it turns out that whichever way you take 17, there are 3 vertices. There's a vertex of degree 3, right? So that is the problem that we are interested in, right? You take what is the smallest possible value of the max degree of H, where H is an induced subgraph of the n-dimensional hypercube with 1 more than half the vertices. So 2 power n minus 1 plus 1 vertices. Right? And here it's just written in math notation. It's a min-max problem. Minimum over all such H of the size and the max degree. Right? So hopefully this is clear. Any questions so far? The problem statement, I suppose it's clear. Okay, so let's denote this problem by the star problem. And this was studied in 88 by Chung, Furedi, Graham, and Seymour, even before the sensitivity conjecture was posed. Okay, and they showed that the answer to this question, they proved 2 results. The answer to this question is at least log n. Right? Every vertex into subgraph of 2 power n minus 1 plus 1 vertices has degree at least constant log n. And then they actually showed that a specific vertex into subgraph of this many vertices that has max degree square root n. So they said that the star is at least log n and at most square root n, right? At least constant times log n and at most square root n. So that is what they showed. So let's quickly see the proof of the upper bound. I'll not show the proof of the lower bound. So it may be clear that there is a correspondence between vertices of a hypercube, Boolean hypercube, and subsets of n. So by n I mean this, which is used to denote 1, 2 up to n. So there is a correspondence between vertices of a hypercube and subsets of this, right? So the ones denote the subsets correspond to 1. So 1, 1, 0 or 1, 1, 0, 0, 0 indicates the set 1, 2. So 1 and 2 coordinates are 1 and the rest is 0. Right? So now let n be partitioned into square root n parts, each of size square root n. So think of n as a perfect square. The proof works in general, but to illustrate the proof, it's easy to assume that n is a perfect square. And we partition into f1 to f square root n, with each fi of size square root n, and let x be the following set of points. Okay, x be the points that are even sets that contain some of at least one of these FIs. Even sets meaning sets of even cardinality, or odd sets that do not contain any of these FIs. Okay, so x is the set of these points, and the claim is that when you look at exactly the graph induced by x, the degree is actually equal to square root n, and the size of x is also equal to 2 power n minus 1 plus 1. Right. So let's just see why this is true, or why it is the degree is square root n. So consider an even set that contains one of these FIs. Okay. Now the neighbor of that point is like 1 with Hamming distance 1, meaning some 0 is changed to 1, or some 1 in that Boolean vector is changed to 0. Right. So it's an even set that contains, let's say, if it contains more than one FI, or let's say you change a 0 to 1, right? It becomes an odd set. But by changing a 0 to 1, you're still you're becoming a superset. So it's an odd set that contains the same FI. So that will take it out of X. Right? So it is not contributing to the degree. And if you change a 1 to 0, and it becomes an odd set. And if it contains more than one FI, then even changing 1 to 0 will still include some FI. So it will not be an odd set that does not contain any FI. But if it's an even set that contains exactly one FI, then if you flip that FI, right? If you flip any one in that FI, it will become an odd set that does not contain any FI. So since FI is of size square root n, there are square root n possibilities for you to move to an odd set that does not contain any FI. So what I'm saying is that x is so if x came, or a point came from the first part of x, it has degree square root n. And if you look at the second part, it's similar. So what this argument is similar, so I'm not elaborating on it. So what we can show by similar argument is that the max degree of the graph induced by x, and also the max degree of the graph induced by x complement, right? Even sets that do not contain FI and odd sets that contain FI, both are square root n. And you can do some inclusion exclusion type argument to enumerate the size of x, and depending on the parity of n, it is 2 power n minus 1 plus or minus 1. Okay. So basically they showed, and this is the proof of the upper bound. This is the proof, but the details have to be written down. Qn, so this is the specific subgraph that has maximum degree square root n, right? And lower bound I'm not showing, but this shows that the answer to the starred question above, it is at least some constant times log n, and at most square root n. So there's a gap here. Okay, there's a gap here, and what Huang showed is that he closed the gap and showed that every vertex induced subgraph of this many vertices has a vertex, contains a vertex of at least degree square root n, or degree at least square root n. So the answer to the first part, the lower bound is also square root n. So which means the answer to the start question is exactly equal to square root n. Right? Any questions so far? Okay. So this is the statement, and this is the proof. This is the statement, and we will see the proof first before getting into what sensitivity is and how it is connected to sensitivity. Right? So it turns out that this combinatorial question is equivalent to the sensitivity conjecture. Okay. So the first part is something that I suppose most of the audience may be familiar with, but I'll explain the proof anyway. Let G be a graph, and let lambda 1 be the largest eigenvalue of A, where A is the adjacency matrix. So I hope all of you are familiar with what is an adjacency matrix. It's a matrix that represents the graph, indexed by the rows and columns indexed by the vertices, and the ijth entry is 0 if there is no h from I to j, and 1 if there is an h from I to j. right? It's an undirected graph, so it's a symmetric matrix as well. In that case, the max degree of the graph, delta G, so delta is used to denote the max degree, is at least the largest eigenvalue. So let's see why that is the case. Let V be an eigenvector corresponding to lambda 1. So let boldface V be then eigenvector corresponding to lambda 1, the largest eigenvalue. Now let Vi be an entry of V with the largest absolute value. Now we have lambda 1 V equal to A times V, because that's a definition of eigenvector. Lambda 1 V equal to A times V. Now you can look at the ith index of lambda 1 V and A times V. Both of them also have to be equal, and they've also taken absolute values. And what is A times V? A times V, the ith index of A times V is just nothing but you are in the ith row of A, you are looking at which are the columns that have 1. They are exactly those columns that are adjacent to I, those j's that are adjacent to I. So it's a summation over all j's that are adjacent to I, Vj, and absolute value again. And this is upper bounded by the max degree times absolute value of Vi. Right? Why is that? Because each of Vj is upper bounded by Vi, because Vi is the entry with the largest absolute value. And the number of neighbors of I is upper bounded by the max degree of the graph. Right? So delta G. Right? So this gives us a lower bound on the max degree of the graph. Right? So this happens to be this lemma, which is somewhat standard, happens to be the first ingredient of the proof. Right? So our goal is to show a lower bound on the max degree of the graph. And what Huang observed is that it is enough to show a lower bound on the largest eigenvalue of the graph. Right? And in fact, you can actually infer more from this. We'll come back to from this lemma. We'll come back to this sometime. Right? So now our goal is we will try to lower bound the largest eigenvalue of the graph H, which is of size 2 power n minus 1 plus 1. Right? And the second ingredient is the Cauchy's interlacing theorem, which is that if A is a symmetric matrix and B is a principal submatrix. So principal submatrix means you have to take the same. Let's say you take a submatrix of A that contains the first, third, and 10th rows of A. Then we also have to take the first, third, and 10th columns of A. Right? So that is what I mean by a principal submatrix. So let's say B is a principal submatrix of A of size m, right? And let the eigenvalues of A be lambda 1 up to lambda n in the decreasing order or non-increasing order, and the eigenvalues of B be mu 1 to mu m. Then these eigenvalues interlace. In other words, the largest eigenvalue of B is upper bounded by the largest eigenvalue of A. Not just that, the ith largest eigenvalue of B lies between the ith largest eigenvalue of A, or at most the ith largest eigenvalue, and the jth smallest eigenvalue of B is at least the jth smallest eigenvalue of A. Okay. I hope this is clear. The statement is clear. I'm not going to prove this. It has a fairly somewhat of a standard proof by one of the characterizations of the eigenvalue. So there is a max-min characterization of eigenvalue from which this follows. Okay, so now let's try to recall what we want to show. We want to show a lower bound on the max degree of H, where H is a subgraph of induced subgraph of the hypercube of size 2 power n minus 1 plus 1. Right? We want to lower bound the max degree of this. So this corresponds to a principal. The adjacency matrix of H will be a principal submatrix of the adjacency matrix of Q of size, so where m corresponds to 2 power n minus 1 plus 1. And in the previous slide we saw this result that it is enough to lower bound the largest eigenvalue of H. But in terms of the eigenvalues of the hypercube, the interlacing theorem tells us that it is enough. So the largest eigenvalue of h, that is mu of h, will be at least the 2 power n minus 1th eigenvalue of the hypercube, right, because of the interlacing. So what we are going to we are noting here is that h is an induced subgraph of 2 power n minus 1 plus 1 vertices, and the largest eigenvalue of h is at least the 2 power n minus 1 largest eigenvalue of the Boolean hypercube, right? And it is enough to lower bound this quantity instead, the 2 power n minus 1 eigenvalue of 2 power n minus 1 largest eigenvalue of the Boolean hypercube. So notice that I am doing some kind of notation abuse. I am using Qn for both the adjacency matrix as well as the graph now. And what are the eigenvalues of Qn? The eigenvalues of Qn are n with multiplicity n choose 0, n minus 2 with multiplicity n choose 1, and so on, up to minus n with multiplicity n choose n. And depending on whether n is even or odd, we get that the 2 power n minus 1th eigenvalue of Qn to be either 0 or 1. So which gives a lower bound on the max degree of h to be 0 or 1. Okay. So lower bound on the max degree of h is either 0 or 1. Again, we don't want this. We want the lower bound of square root n, but this is some start. This is some start. Any questions till now? Okay, so we are interested in h, which is 2 power n minus 1 plus 1 induced subgraph of the Boolean hypercube. We first said that when we want to lower bound the max degree of h, we first said that it is lower bounded by the eigenvalue of h, and then we are saying it is lower bounded by the 2 power n minus 1th eigenvalue of Qn. But even that does not seem to be enough. So now we bring the third ingredient of the proof, which is the signed adjacency matrix. So by signed adjacency matrix, what I mean is you take the adjacency matrix and you change you attribute signs to some of the entries. Okay. And the only thing is that I want it to be symmetric still. So if I make the ijth entry from plus 1 to minus 1, I also want to make the jith entry from plus 1 to minus 1. So, but consider a matrix M which is a signed adjacency matrix, meaning I just change some plus 1s to minus 1, retaining the symmetricity of the matrix. Right? And even in this graph, even in this matrix M, lambda 1 turns out to be a lower bound of the max degree of G. Right? So earlier I said that lambda 1 of the adjacency matrix is a lower bound of the max degree. Now I am saying that you take the adjacency matrix, you change the signs of some entries, even then the eigenvalue will be a lower bound on the max degrees. And the proof happens to be exactly the same. Everything is the same. In fact, some of the absolute values that I had for the earlier statement were not really necessary, but in this case we may need it. So it's exactly the same. I think every argument is exactly the same, because the summation of Vj is at most max degree times the largest entry in the eigenvector, which is absolute value of Vi. So the proof is exactly the same. So now our task boils down to finding a signing of the adjacency matrix of Qn such that the 2 power n minus 1th largest eigenvalue of that signing that the matrix with that signing is square root n. Okay? Because the eigenvalues of Q itself, the 2 power n minus 1 largest eigenvalue was 0 or 1, but we want to assign signs in such a way that the 2 power n minus 1 largest eigenvalue is square root n. Yeah, that's the goal. and that's the rest of the proof. So let me first describe the adjacency matrix of the Boolean hypercube, and then I will describe the signing. Okay. So Q1 is the one-dimensional Boolean hypercube with just an edge, right? So it has adjacency matrix as given here, and Q2 it is like another edge. Basically, you have two copies of Q1, right? You can view it as two copies of Q1, and made adjacent by you connect them to each other, right? So yeah, you connect them to each other. So what is happening here is that you have two copies of Q1 and then you make adjacent to each other. So just like that, you can look at the matrix Qn as two copies of Qn minus 1, and then you have identity matrices. So I2n minus 1, I2n minus 1, which connect the corresponding vertices and make them adjacent. So the next stage would be something like this, and then you will connect something like this, right? So this is the hypercube. So the identity matrices denote the connecting the corresponding pairs. Q denotes the two copies of the Qn minus 1. Okay. So this is adjacency matrix of Qn, and for obtaining the bound, what one considers, you start with the same single edge, and you go to this matrix where the one copy of Qn or one copy of the original graph is given a negative sign. Okay, so this is applied recursively. So yeah, some entries will see the negative sign multiple times, right? But this is how it is. Okay. Now let's calculate the eigenvalues of m. Recall that our task is now to show that the 2 power n minus 1 eigenvalue of m is square root n, or at least square root. So let's consider mn squared. So you can write it in the block, in the same inductive block form, and you can see that the off diagonal blocks are 0 because they cancel each other, and the diagonal blocks are mn minus 1 squared plus identity matrix, both the top left and bottom right diagonal entries. But by induction, mn minus 1 whole squared is n minus 1 times identity matrix, plus identity matrix gives you n times identity matrix. So this gives you n times identity matrix. So mn squared is n times identity matrix. Or in other words, another way to say the same thing is that all the rows of mn are orthogonal to each other. So this is also another way to note this. So mn squared is n times the identity matrix. This means that this also means that the eigenvalues of m are plus or minus square root of n, right? Because let's say take an eigenvector v and you apply m to it twice. So you will get, one way to see it is that you will get lambda square v, where lambda is eigenvalue. Another way to view it is that it is m squared. It is m squared v, which is n times iv, which is actually n times v, right? So lambda squared has to be n. So the eigenvalues of m is going to be plus or minus square root n. So all the eigenvalues are plus or minus square root n. But how are they distributed? How many plus square root n's and how many minus square root n's? It's also not hard to see that this matrix is all the diagonal entries of this matrix is 0. So the trace of mn is going to be 0, and trace also happens to be the sum of the eigenvalues. So the sum of the eigenvalues is also going to be 0, which means exactly half the eigenvalues are square root n and exactly half the eigenvalues are minus square root n. So the multiplicity of both the eigenvalues is 2 power n minus 1. which means that the 2 power n minus 1, the largest eigenvalue, is also square root n, and which is what we wanted. We want to show that the 2 power n minus 1 largest eigenvalue was square root n. So this signing just happens to work. And this is the proof of the combinatorial question, which happens to be equivalent to the sensitivity conjecture. Any questions so far? I haven't had any questions. So if there are any questions, we'll be happy to answer. Okay, I think I'll move on. So, so you can just see that all the steps so far have been rather simple, elementary, straightforward. The only somewhat of an involved step is the Cauchy's interlacing theorem, which actually can be sidestepped. Okay, so one thing that I would like to note is that after this was proven, this result was proved. This generated a lot of attention because of the simplicity and the brevity of the proof, as I said before. So this generated a lot of internet discussion, and a computer scientist by the name Scott Aronson runs a very nice blog where he blogged about it, and it generated discussion in the comment section. So there is a comment by a commenter, which was later elaborated by Donald Knuth, on how you can avoid the interlacing theorem altogether and get a direct proof to show that the signed adjacency matrix of any H has a eigenvector, has an eigenvalue, or has an eigenvalue of at least square root n. Right? So I'm not going to go through this entire proof, but this is even simpler than interlacing theorem. If you consider interlacing theorem to be advanced, this only uses the fact that a system of equations with let's say k minus 1 equations and k variables, and you can always find a way to you can always find a way to solve them, right? So in a very, very high level. Right, so you can also avoid that and use that argument to produce an eigenvalue, eigenvector for H of eigenvalue at least square root n. The matrix that you start with is the same. It's the same matrix with the same signing. Right? So we start with the fact that M has its eigenvalue of at least square root n, but we don't use the interlacing theorem to show that H also has an eigenvalue of square root n. Okay, so just some explanation as to how he may have arrived at this signed matrix, right? So there is this Hadamard's inequality, which states that determinant of any matrix, the absolute value of the determinant, is upper bounded by the product of the norms of the vectors involved in it, and equality achieved only when all the vectors are orthogonal. Right? One way to, or one implication of this is that if you look at a rectangle, the volume of the rectangle, or the area of the rectangle, is length into breadth, right? So which is equality, that the length into breadth are orthogonal. But if you look at a parallelogram, the area is less than the length into breadth, right? So this is, or even if you look at a three-dimensional parallelepiped, the volume, the determinant corresponds to the volume. It is at most the product of the lengths of the sides. And equality happens when it becomes a orthogonal thing, like a cuboid. So this is Hadamard's inequality. And so Mn is a signed adjacency matrix of Qn. So whatever signing we take, we know that the all the rows have square root n once, because the Boolean hypercube has degree square root n. sorry, it has degree n, so the norms is square root n, right? So the determinant is at most square root n power 2 power n, right? And but we want the 2 power n minus 1 largest eigenvalue to be square root n. This, along with the fact that it's a bipartite graph, so the eigenvalues have to be symmetric about 0, together imply that each eigenvalue has to have degree, has to have absolute value at least square root n. So the determinant of the desired matrix, whatever we are looking for, also should be at least square root n whole power 2 power n. So because of this matching inequalities, we get that the determinant has to be equal to this, which is equal to the bound given by the Hadamard's inequality, which means that it has to be orthogonal. All the rows have to be orthogonal, right? So which means m times m transpose has to be some identity matrix times something, and the rest is just some basic trial and error will give us this particular sign. There is not much scope for getting a different signing. This is the only signing that seems to work. Modulo just changing all the signs of a row or something like that. So modulo some simple transformations, you will get roughly this is the only signing that seems to work. Okay, and I'd like to once again ask if there are any questions. Because there are no questions, I will move to defining what is sensitivity and why it is significant and how it is connected to what we just saw. Okay, so maybe I'll go ahead.
Excuse me, sir.
Sure.
Sir, actually it's not a question, it's just a small doubt. So we are in order to prove that the bound lambda 1 h is less than equals to root n. So we are attacking on the maximum eigenvalue of the graph.
We want to show that the degree of the max degree of the graph is at least square root n.
Yes, right.
And we note that the maximum degree of the graph is at least the largest eigenvalue.
Yeah, right. So
then it is enough to show that the maximum eigenvalue is at least square root n.
Okay.
Is that clear?
Yes, sir. Right.
Now, so that is the first step. But then maximum eigenvalue of h itself is not very clear, because it could be any subgraph.
Yes.
Or induced subgraph. So then we show this general interlacing thing that by the interlacing, for any h, the largest eigenvalue of h is at least the 2 power n minus 1th largest eigenvalue of the Boolean hypercube.
Okay.
Yeah.
Right.
But the 2 power n minus 1th largest eigenvalue of the Boolean hypercube happens to be 0 or 1. So that is not quite enough. So then we note that it is enough to consider a signing of the Boolean hypercube. So then we consider this signing, where we assign signs to some vertices in the Boolean hypercube, not vertices, edges in the Boolean hypercube, correspondingly signs to some entries of the adjacency matrix, and show that this signed adjacency matrix, the 2 power n minus 1th eigenvalue of this signed adjacency matrix, has eigenvalue the 2 power n minus 1th eigenvalue of the signed adjacency matrix is square root n.
Okay, sir. And here mn square is equals to n I to n. So here we are recursively applying this.
Yes. So this is an inductive kind of proof.
Okay.
So it is easy to see that m1 squared. So it is a somewhat of an inconsistency in the notation. By mn I denote the nth matrix, but then each one of them is mn is a 2 power n cross 2 power n matrix. So that's why I'm writing 2 power n is subscript of I. So M1 squared is just identity matrix.
Identity matrix, right.
So that's the base case. Now Mn squared is Mn minus, so you can view it as a product of the blocks here. Mn minus 1 squared plus I times I is I again. And the off diagonal things cancel because it's M times I and I times minus M, so that cancels. And same here for this one as well, this 0 as well. And this one is symmetric, it's minus M times, sorry, I times I and minus M times minus M, so that's also the same. And inductively, we can assume that M minus 1 squared is N minus 1 times the identity matrix.
Identity.
Yeah.
Yes,
so assume that, sorry, M minus 1 squared is equal to N minus 1 times the identity matrix. I 2 power N minus 1, sorry, I'm just running out of space. So that 2 power N minus 1 times N minus 1.
Yes, sir, now it is clear.
Yeah.
Thank you, sir.
Yeah, thanks for the question. Any other questions? Okay, I'll move on. If there are questions, feel free to ask. Let's see what is sensitivity of Boolean functions and why it was studied. And so Boolean function is a function from n length n bit Boolean vectors to 0, 1, right? Or equivalently, we could think of it as assigning 0 or 1 to the vertices of the Boolean hyperplane. Okay, so given a Boolean function, the local sensitivity is you look at the function at a value x and see for how many you flip the bits, input bits. Okay. For how many such flips does the function value change? This is the local sensitivity of f of x. Okay, so local sensitivity of f is at x is the number of indices upon whose flipping the function value changes, and the sensitivity is the maximum over all x, the local sensitivity. Okay, so x superscript I is the x with the ith bit flipped. So some examples, consider the AND function. AND function is 1 if and only if all the input bits are 1. So consider AND function the local sensitivity at the all zeros input. At the all zeros input, you flip any input bit, the 0 will become 1, but the output will not change because there still are many zeros. So the AND function at the all zeros input has sensitivity 0. But consider the AND function at the all ones input. At the all ones input, the AND function is 1. But if you flip any input bit from 1 to 0, the output value changes from 1 to 0. So which means the AND function has local sensitivity n at the all ones input. So the local sensitivity of AND function at the all ones input is equal to n. Right? And since the local sensitivity, since n is the maximum number of indices that we have, that means the sensitivity is maximized at that value. So sensitivity of AND function is equal to n. OR function is also similar. OR function is most sensitive at the all zeros input, because any all zeros input, the OR function is 0. But if you flip any input from 0 to 1, the output flips from 0 to 1. So the sensitivity of the OR function is equal to n. XOR function or the parity function, that's also sensitivity equal to n, but the local sensitivity is equal to n at any x. So whichever x you are in, you flip any input bit at any index, the output value is going to change because the parity will change whenever you change any 0 to 1 or 1 to 0. So the XOR function over n bits, the sensitivity is equal to n. In fact, the local sensitivity is n everywhere. Consider just one more function, f of x equal to x1, right, the first coordinate. Sometimes it's called the dictator function. this has sensitivity equal to 1 because the output will change if you flip the first bit. The output will not change if you flip anything else. So at any x, the sensitivity is equal to 1. And local sensitivity is 1, so sensitivity is equal to 1 as well. This is the definition of sensitivity. So now let's define block sensitivity. Block sensitivity is defined very similarly, but instead of allowing or instead of saying you flip input bits, we flip blocks of input bits. Okay, so what if we flip blocks? Suppose disjoint. So we need to flip disjoint blocks of input bits such that flipping of any, like all the bits in the blocks. Let's say the blocks are B1 up to Bk. If you flip all the bits in B1, the output has to flip. All the bits in B2, the output has to flip, and so on. So the maximum number of blocks to which we can divide the indices. So these blocks need not be contiguous, but they have to be disjoint, and they need not be a partition. Like there could be some leftover indices that are not part of any block. Okay. So if there are k blocks upon whose flipping the function value changes, then we will say that the local block sensitivity is k. And block sensitivity in an analogous manner is defined as the maximum amongst all the local block sensitivity, maximum over all the values x. Right? So is the definition is clear? Sensitivity and block sensitivity. Okay. And one thing that is easy to note is that sensitivity is a special case of block sensitivity, because one way to divide the indices into blocks is by considering singleton blocks. Right? So when you consider singleton blocks, you're just looking at sensitivity. So the block sensitivity is always lower bounded by the sensitivity, because you can always consider singleton blocks. And block sensitivity is also upper bounded by n, because you cannot make more blocks than there are indices. And when f is non-constant, sensitivity is at least 1. Right? So we have this set of inequalities. And because of this, we already saw that sensitivity of and, or, x, or everything is equal to n, which means the block sensitivity is also n for each of these functions. So we have a lower bound for block sensitivity in terms of sensitivity. So one question that one may ask is, can we get an upper bound for block sensitivity in terms of sensitivity? And this is the sensitivity conjecture. Nissan and Szegedy stated that block sensitivity is upper bounded by some polynomial of sensitivity, or in other words, some constant. It is equal. It is at most sensitivity power some constant, right? For any Boolean function, and this is the sensitivity conjecture that they posed in 1992. So we know that sensitivity is a lower bound, and they claim that it's less than or equal to sensitivity whole power some constant. And this is the famous sensitivity conjecture, which remained open till roughly 2 years back. Some history. The study of sensitivity started by Cook, Dwork, and Leschuk in 86. They were studying what is called Crew-Pram model, which is some computational model where you can read parallelly, some parallel computation model. You are allowed to read in parallel, but write cannot be done in parallel. Okay, and so crew of f is the computation cost of computing a Boolean function in this model. Right? So they showed that the crew of f is lower bounded by log of the sensitivity, and later Nissan showed that the crew of f is theta of log block sensitivity. Okay, so first it was shown log of s is a lower bound, log of sensitivity is a lower bound, and then it was tightly related to log of block sensitivity. And later Nissan and Szegedy showed that there are several complexity parameters that are polynomially related, right? So such as block sensitivity, degree, randomized query complexity, and so on. So one or two I just mentioned. So decision tree means given a vector x, you can make queries like you can ask like, is the first bit 1? If the first bit is 1, you look at the 10th bit. If the first bit is 0, you look at the second bit, and so on. And that kind of and finally you have leaves where you say that the function is 0, 1, and whatever. So the decision tree complexity is the minimum over all decision trees, the depth of the decision tree. Right? Another complexity measure of a function is a degree. So given any Boolean function, you can represent it as a real polynomial. So in the Boolean values, in the 0, 1 values, this polynomial should give the same value as a function. Right? So this is the degree of the function, and so on. There is approximate degree, certificate complexity, and so on. So these are all different complexity parameters. And what Nissan and Segedi showed is that all of these parameters are polynomially related. Meaning, so take S1, which is one parameter, and S2, which is another parameter of the function. So there is one polynomial that is lower bounding S1 and upper bounding S1 in terms of S2. So take any two of them, they are polynomially related. And what remained outside this group is the sensitivity. So it may seem kind of strange that blocks and the natural inclination, for at least for me, is to think of sensitivity as a natural parameter and block sensitivity as a made up artificial thing. But surprisingly, block sensitivity was easy to show that it is polynomially related to all of this, and sensitivity still remained outside this group till the conjecture was resolved. And the resolution of the conjecture placed sensitivity also amongst these other parameters, right? And yeah, any questions so far? Definitions of sensitivity, block sensitivity, anything? Okay, maybe I'll just explain one result that shows that one function where the block sensitivity is at least square of the sensitivity, which implies that this constant C, as stated in the conjecture, should be at least 2. Okay, so we'll see a function. It's called a Rubinstein function. So for this function, it will be helpful to view f from n square bits to 1 bit, okay, because we would like the view the bits input bits as a square. Okay, so the f function of the function is an OR of the g function for each row, right? So there are n rows, and f is an OR of the g function on each of these rows. So what is the g function of each of these rows? The g function on a row is 1 if and only if there are 2 bits equal to 1, 2 adjacent bits equal to 1, and everything else equal to 0. So here, now here n is equal to 4, right? There are n square is 16. All the rows give 0 because it is not of the form. The g function is equal to 1 only when you have something like this. Something there has you 2 adjacent ones and everything else 0. So here all of them are 0. So all the g functions are zeros, and the f function is the OR of all of that, which is also 0. But let's consider this: the first 2 bits, if we make it 1, the first row gives output 1, the g function gives output 1, and the f also gives output 1 because it's an OR. Now look at the second 2 bits. Even then, the first row gives output 1, and the OR function also gives output 1. Now you look at these 2 bits. Even now, the second row gives output 1, and the OR function gives output 1. And now you see the pattern. Now you can divide all the rows into n by 2 such blocks, each block having 2 bits, and you see that the block sensitivity at the all zeros input is equal to n squared by 2 roughly, right? So it will be slightly less when n is odd, but still it is some constant times n squared. or some omega n squared. Right? So at the all zeros input, the function is 0. This is Rubinstein function, but we are demonstrating a block, n squared blocks, where the output becomes 1. Upon whose flipping the output will become 1. So the block sensitivity is n squared, at least n squared, right? And now we'll see that the sensitivity is at most order n. So the two cases, depending on whether the function is 0 or the function is 1. So if the function is 0, it's an OR of all the rows, right? So each row must output 0. When each row outputs 0, there are at most two possibilities, or at most two sensitive coordinates. And that happens when a row contains only 1 1, or the row contains 3 1s, exactly 3 1s consecutively. In each case, the red bits denote the sensitive indices. So each row can have at most two sensitive coordinates if each row outputs 0. When the function is 1, then if two rows output 1, then the sensitivity is 0, because you can at most flip 1 bit. So even if you flip one of the rows output, you change one of the rows outputs, the function value will still be 1. If exactly one row output 1, then the worst it is possible is that this row that outputs 1 it's sensitive everywhere, which means the number of bits in that row is also n. So again, the sensitivity is at most n. So we have seen that the sensitivity, block sensitivity, is at least some constant times n squared, and the sensitivity is at most order n. So this is an example of a function whose block sensitivity is at least quadratic in the sensitivity. And before the resolution of this conjecture, what was known is that block sensitivity is like the upper bounds available were all exponential blocks of upper bounds of block sensitivity in terms of sensitivity. Right? So you can see 4 power sensitivity, e power sensitivity, 2 power sensitivity, and so on. And the gap that is known, meaning a concrete example of a function such that this function has block sensitivity at least this much. Right? The first one is the Rubinstein function, which we saw to be of the order of SF squared. And this was only marginally improved over the years. So it's half, 2/3, but it's all quadratic. You can see that till the resolution, the upper bounds were all exponential and the lower bounds were all quadratic. And what the proof of Huang would imply is that block sensitivity is equal to some constant times sensitivity whole power 4. So from the exponential upper bounds, we get a 4th power upper bound, which is way better. And it's close to 5:30. So how long do I have?
Yeah, another 10 to 15 minutes.
Okay, so I'll very quickly explain the equivalence and then conclude. Yeah, thanks. Okay, so the equivalence, even this equivalence was known as early as 1992. So when I'm saying equivalence, meaning we saw this combinatorial problem, and now I'm talking about sensitivity. And till now, it seems like they don't have any connection. And what is the reason for the connection is what I'm going to explain. And this was proved in 1992 by Bartzman and Boolean. And so everybody who attempted this conjecture over the years also had access to this equivalence, and despite that, they were not able to show the proof. But let's see. So what they say is that for any induced subgraph of the n-dimensional Boolean hypercube, such that the induced subgraph does not have is not exactly half the vertices, right? It could be more or less. You look at the max degrees of H and max degrees of the H complement and look at the maximum of these two. Suppose we can show that this is at least Hn, where H is some function, okay? And then in that case, we have that the sensitivity of the any Boolean function is at least H of the degree of F. So here the degree denotes the degree complexity of that function when written as a real polynomial. Okay. So what they said is that if there is a small h such that the max of the degrees of any induced subgraph of vertices not equal to 2 power n minus 1 vertices is at least small h, then the sensitivity of any Boolean function is at least h of the degree. The degree denotes the uh, degree complexity of the function. And it was already known, as I said earlier, all these parameters were already known to be polynomially related. That block sensitivity of any function f is at most 2 times the degree of that function, 2 times the degree squared of that function, right? And what Huang showed is that the part in red, he showed that with hn equal to square root n. We showed that for any Boolean hypercube, or for any for any induced subgraph of a Boolean hypercube, there is the max degree is at least square root n. So h was square root n, right? Which means the sensitivity is at least square root of the degree, which means degree is at most sensitivity squared. And here we have block sensitivity is at most 2 times degree squared. And when we add the degrees at most sensitivity squared, we get that block sensitivity is at most 2 times the degree sensitivity to the power 4, right? And that is the relation. So Wang showed that every every vertex induced subgraph has a vertex of degree at least square root n. So sensitivity is at least degree, which means degree is at most square of sensitivity. So we get the block sensitivity is at most 2 times the sensitivity square, sensitivity to the power 4. One comment is that the relation between sensitivity and degree is tight. So in that sense, Huang's proof is a tight. There are functions, for instance, the AND of OR functions. So if you write n as a square of, if you view n as a square root n rows of square root n bits, and you take ORs of all the rows and then AND of all the results. This gives a degree n but sensitivity of square root n. So this is tight. However, the result is that block sensitivity is at most twice the sensitivity to the power 4 is the upper bound. But the tight examples that we know are all quadratic. So we know examples of functions where block sensitivity is equal to square of the sensitivity. So this is still, there is a gap. We don't know which is the correct number. Are there functions for which block sensitivity is 4th power of the sensitivity, or is that there is a proof that shows block sensitivity is at most square of or quadratic in sensitivity? The next thing that I have in my slides is the proof of this equivalence, which I think I will skip. So basically, it boils down to the fact that, so maybe I'll just explain just one point. Fact that suppose this is a Boolean function. So let's say the red indicates zeros and green indicates 1. Right? So, and so you can suppose you flip all the odd parity values. So that is, you flip all the odd parity values. Right? Now, the sensitivity checked how many edges are there from red to green. Let's say at this node, let's say all 0 nodes, there are 3 edges that go to green. But when you flip all the odd parity vertices, now all of them become red. So basically, it turns into the max degree of the induced graph on red or the max degree of the induced graph on green. This is simply because every edge connects an odd parity and an even parity vertex. So any edge that contributes to local sensitivity will now become both red or both green, both endpoints red or green, which will contribute to the degree of the reds, the induced graph by the red vertices or the green vertices, and that is the main idea of the proof, which I will not elaborate. Just some final thoughts that I want to just say. This was in the words of Huang himself. So he says that he saw the problem first in 2012 after his PhD or sometime during his postdoc. And first he looked at the eigenvalue and so on. And what is noteworthy here is this comment, the last bullet point, that he kept going back to this conjecture whenever he thought he had a new trick in his disposal, right? At his disposal. Whenever he thought there was a new approach, he just kept going back to it again and again and again, persisting on the problem. Right? And this is, I think, this shows the value of the persistence, and which is something incredibly important to all researchers, right? So it's not merely about being smart and brilliant. It's also one has to keep hitting at the problem again and again and again and sometimes that is what is required to make progress, right? So he kept working on it till suddenly one fine night he understood the idea that the signed adjacency matrix also happens to work. And I read this at a couple of places that the key ingredient that seemed to have eluded many people over the years, because all the ingredients are all somewhat standard and elementary, is the idea of taking the signed adjacency matrix and noting that even that seems to be good enough to provide the necessary lower bound. And some open questions that are there in Huang's paper. So one is what I already mentioned. There is a gap between the upper bound, the relation between block sensitivity and sensitivity. Another one is we saw that any 2 power n minus 1 plus 1 vertices, there is a vertex of degree at least square root n. Now, suppose you want a vertex of degree at least square n power 0.6. How many vertices should you choose? Should you have to choose? That's one question. Another one is 2 power n minus 1 happens to be the size of the largest independent set of the Boolean hypercube. Now you could ask a question on other graphs, not the Boolean hypercube. So for any graph G, let alpha G be the independence number, the size of the largest independent set. Right. Now, if you take one more vertex than the size of the independent set, what can we say in general about the max degree of such a graph? So in a way, generalizing this question to other graphs. There has been some work, I think, on some special classes of graphs, but I think there are still other graphs for which this can be attempted. And yeah, I think that's about what I wanted to say. This is just leaving you with a tweet, just to again emphasize how short the proof was by Ryan O'Donnell. He just wrote it up as 2 exercises. Yeah, and yeah, that's about it. Yeah, thanks.
Yeah. Thank you, Subruk, for the interesting talk. Yeah. Audience, if you have any question, we can ask. Okay, in this open problem, you mentioned for n power c, c greater than half.
Right.
Is there any improvements, any particular cases?
Not to my knowledge, no.
Yeah.
So we're asking if you want n power 0.6, how many vertices should we go through, right? Yeah, not to my knowledge.
Okay. Is local sensitivity what you have defined for a Boolean formula? Measuring the sensitivity, we can think of that as a decision problem, and we can think about the complexity of the problem, right? Given a function.
I'm not quite. I'm not able to follow the question. So can you please repeat?
That measuring the sensitivity of a formula, the Boolean formula.
Okay.
Like you have mentioned here for and R. For a general formula, let us take, like general combination of Boolean variables, let us take. So for that, like computing the sensitivity, what will be the complexity of that?
Okay, I've not thought about that like that, because sensitivity is, so the way I've thought about, I've not thought to this question. So you're asking, given a Boolean function, how do you compute the sensitivity?
Yes.
It will also depend on, so how is it given? The Boolean function, if it's given as a truth table, then it may not be that, there could be a polynomial time algorithm, right? Because the truth table itself will have 2 power n points or whatever. So I think there could be polynomial time algorithm. I don't think this is a very, this is something that that is interesting. I think that's not, given us, I think if you have a truth table, I think we have a straightforward algorithm to measure it. I think you just check the local sensitivity and then then compute the max. It's about that. Yeah.
Are there other questions? Okay, if not, thank you, Subruk, for the interesting talk. Yeah.
Sure, thanks. Thanks, Ajay, and thanks all for